So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Will Grundy, who's come across to us from the Lowell Observatory. Will did his undergraduate studies at Yale and then moved to the Lunar and Planetary Laboratory, where he did his PhD in the University of Arizona. His supervisor there was Uwe Fink. And then he did a postdoc at Grenoble, where he worked with Bernhard Schmidt. And got his hands dirty in laboratory ice investigations. He then did a Hubble Fellowship at the Lowell Observatory and then joined the observatory staff in 1997. His work has focused on spectroscopy of ices and interesting things that are going on in and around the Kuiper Belt. He also, in addition to that, he's the custodian of an online collection of French cheeses on his website, if you're interested in that subject. And it being lunchtime, I'm sure there will be a few people who might want to check that out on their iPhone. And he has published in the areas of ices and spectroscopy, as I was mentioning, temperature-dependent spectroscopy of ices, such as nitrogen, hexagonal H2O ice. These have applications, for example, in Triton and Pluto. He's also interested in the evolution and solar gardening of ices in Kuiper Belt objects. And he was responsible for the discovery of CO2 ice on Ariel and has published on H2O ices on Umbriel, Titania, and Oberon. And he was the lead author on a recent publication on New Horizons, which we're going to hear about, on mapping of Europa and Ganymede as New Horizons pass by Jupiter. And he is also more recently interested in masses and properties of trans-Neptunian binaries. But today we're going to hear about his interest in spectroscopy of Pluto and how that might help out in the New Horizons mission. So please join me in welcoming Will.
So thanks very much for that kind introduction, and let me just reset my clock here. So I really do appreciate the invite to come here, because there's so many people that I know here that are doing science that I pay such close attention to, and I've never actually visited before, so it's kind of cool to see the place finally. So first of all, why are we even talking about Pluto? Why is it interesting? I think it's a very interesting system, even in complete isolation, which was sort of what we thought it was 20 odd years ago, before more Kuiper Belt objects got discovered. I don't even know what to call it now. It's a double planet in a sense. So does it only have 4 moons then instead of 5? It's a weird place. Of course, we're soon going to have an incredible close-up view from New Horizons in 2015, and so that will stimulate a lot more work. So we're right now in the kind of the hand-waving phase, where we don't really know what we're going to see. It is one of the largest of what I call the planet-sized Kuiper Belt objects, which are the ones that are spherical. So several of these, let's see, can I do that? No, let's see, I have to move my mouse there. Okay, so several of these, Eris, Pluto, Makemake, Quaoar, et cetera, have volatile ices on their surfaces, which means that on very short timescales, they're going to reconfigure their surfaces on seasonal timescales as opposed to geological timescales. So that's kind of fun. You can think about what kind of processes are involved. I think of these really as a third class of planet, where you have your gas giants and you have your rocky terrestrial type planets, and these are a different class. And we'll see one up close, but we won't really be able to do the comparative planetology that we would love to do until we see several of them up close. And that'll be a while, because the outer solar system is far away. I think it would be comparable in size to Orcus, maybe, or it's sort of down there towards the bottom of the list. It's bigger than that. It's like 1,000, isn't it?
Used to be 1,000.
Well, yeah, we'll soon see exactly how big it is. That's true. All right, so I'm a spectroscopist. I like spectra. You know, we're always told never to show wiggly lines at public talks because it puts everyone to sleep, but there is an enormous amount of information in the spectrum, and that's why it's exciting. You see all these species that are labeled, methane, carbon dioxide, carbon monoxide, there's one, nitrogen. So this is Pluto's spectrum, and up here is Triton's spectrum, and they're often plotted together because Triton is our best analog for Pluto prior to the encounter. It will turn out to be very different in interesting ways, I'm sure, but similar in other interesting ways. And just to get you oriented, the visible region is shown off to the left. So we're looking just to the long wavelength edge of the visible and covering a sort of a wider span, at least in terms of wavelength units. And there's a lot of features out there. What we're looking at is reflected sunlight off of the surface. So the geometry is like this, where the sun is illuminating the surface and photons are bouncing around, and some of them are coming in the direction of our spectrometer. And the path that they take through the surface depends on a lot of things: the texture of the surface, the optical constants of the materials. So it's wavelength dependent, and those optical constants are dependent on a lot of different things. So there's potentially a huge amount of information in the spectra, and you model the spectra using various multiple scattering radiative transfer routines, a couple of which are mentioned there. There's lots more where they came from. Now, the reason we're going to be talking about ices is because they're very colorful at these wavelengths, so you can see them. There are also ingredients that probably aren't colorful, and we can't see them, so we're not saying anything about them right now. But you'll notice these are absorption coefficients, and I'm going to have to apologize that sometimes absorption goes up, sometimes it goes down, and I'm pretty much interchangeable about it. And so you just have to, if you see a spike that's going up, you're probably looking at absorption coefficients. If you see a spike that's going down, you're probably looking at reflectance. But look at the units here. See if I can get my mouse back. There it is. These are orders of magnitude. So these are pretty big contrasts over short wavelength region. These things are really amazingly colorful. That's why we know they're there, because they're so colorful. They're easy to detect and see. So just having these contrasts gives you enormous remote sensing potential. Now, I didn't plot argon on here, for instance, because it doesn't have any absorptions in our band. So we can't see argon. It's probably on the surface of Pluto, but we can't see it. So we're not going to say a whole lot about it. But it's there, probably. So we've been observing Pluto with IRTF since 2001. And we're up to something a little over 70 nights usable so far. I'm not counting the ones where we were clouded out or something. And a whole bunch of people have been involved over the years, and the main players are listed there, but there's more. A lot of students have also been involved. The vital stats on the spectroscopy are listed here on the slide, and it's described in excruciating detail in the Icarus paper if you really want the details. People put up representative spectra. These actually are representative because I included the worst and the best in that plot. And so from where you're sitting, you probably can't even see the difference between the worst and the best, but the worst are definitely worse than the best. I can confirm that. And I had to draw the line somewhere. All right, so here's where the sub-Earth point was on Pluto. This is a map, the most recent Hubble Space Telescope map, projected to unroll it. And then I plot in all those green spots the points on the surface that were in the center of the disk when we observed it. So obviously we don't resolve the disk of Pluto because it's like a tenth of an arc second across, and the seeing disk is typically an arc second or a half an arc second or something. So what we see is the entire hemisphere centered on that green dot, and you're averaging over everything. So you don't have great spatial resolution, but you're seeing it. You're seeing different parts of the surface still. And the dashed line is the visible light curve scaled completely arbitrarily, and you can see how it corresponds to the dark spots, corresponds to this light curve minimum, and this bright albedo feature corresponds to the light curve maximum, and then this region called shelf, dating back to the time when all we had was light curves, and it was sort of flat. All right, so we've got 70 spectra. ideally, you would model it in detail using the Hapke theory or whatever your favorite radiative transfer theory is. That's time-consuming, as Christina can tell you. It's a lot of work, so we're going to do quick and dirty stuff for the present talk and get into the modeling in the future, kick it down the road. So we need to figure out quick ways of quantifying an absorption band. So let's say this is an absorption band in reflectance. You can draw a continuum line across the top like you just stretched saran wrap over it or something and integrate under there. And that's a band area, in a sense. It's usually expressed as an equivalent width, which is the width of a square band that contains the same area in whatever strange units your integral gives you. If you don't like the fact that the continuum is stretched over the surface like saran wrap, you could just draw a straight continuum over the highest point you could find. And you can measure the albedo in the center of the band and measure the albedo in the continuum and do a ratio and get a fractional depth of the band. So these are the kinds of things I'm going to be showing you. Once you've got the band quantified in a way like this, you can plot it versus whatever you like. And at least do some quick science. So the first thing is obviously diurnal variations. Pluto's spinning. It's got a 6.4-day period. So as you observe it on different nights, you're seeing more of some areas and less of other areas. So let's start by plotting these kinds of band parameters versus longitude, or sub-Earth longitude. So this is the methane bands. This is 4 of them. There's, as you saw in the spectra earlier, there's a zillion methane bands. So this was just 4 that happened to plot without stepping on each other so much. That was how I chose them. And you can see that they all vary as Pluto rotates in more or less the same sense, although the exact location of the peak might shift around a little bit. But there's a minimum. Let's see, this is fractional depth, so a deeper band is up and a weaker band is down. So there's less absorption here at these longitudes and more absorption here. And you notice that these curves are pretty puffed up. I'll get back to that later because there's some interesting details in there. So moving on to the next ice, this is carbon monoxide ice. That has a much larger amplitude variation as Pluto rotates. It's actually almost a factor of 3 difference between the minimum and the maximum. That's a large contrast. That kind of tells you that the carbon monoxide ice that's forming this band can't really be circumpolar, because if it was circumpolar, you'd be seeing it all the time. It's got to be sort of lower latitudes and pretty heterogeneously distributed in order to see such a big variation. N2 ice is tough because it's right on the edge of this methane band that sort of muddies the water, but it looks like it's showing a similar pattern to the CO ice. So, okay, that kind of makes sense because nitrogen and CO are miscible in one another in the solid phase in any composition. So, and their volatilities are very similar to each other, where methane has a lower volatility. So, yeah, maybe they go together. Okay. There's one other way to get at the N2 ice, which is through the methane bands, because the presence of nitrogen shifts the methane bands subtly. So you can measure that shift and plot that as a function of longitude. And here's those, I think that they might be the same 4 bands. I can't remember for sure now if they are or not. But they also vary systematically. And 0 shift is up at the top now. And so a bigger shift is downward. And you can see that the maximum shift is around 180 degrees, which was about where the maximum N2 and the maximum CO are. So that kind of hangs together. I guess I should have said early on, ignore the points outside 0 to 360 are just duplicated the same points again. So that's just to make it easier to see the pattern. So if you counted those and got more than 72 or whatever our number of nights were, we didn't actually observe that many nights. All right, so let's relate these back to Pluto and the albedo features on the surface. So this is a view of that same Hubble Space Telescope map looking down on the North Pole. So it's a right-hand, I use the right-hand rule coordinate system. Not everybody does. If you go to Horizons, you will not find this yet. It's not even really their fault. It's kind of our fault on the New Horizons team because we're sticking with one coordinate system until we do the encounter and it's safe. But so this is looking down on the summer pole, which I call north and some people call south. So you're looking down on your thumb. All right, 0 degrees is defined as the direction towards Charon, and they're tidally locked. So as far as we know, that's a fixed place, although if there's some libration or something going on that we don't know about, maybe it's a little more complicated. 90 degrees east corresponds to that large dark area on the equator that made the light curve minimum. 180 corresponds to where that bright spot was, which is also where we were seeing the N2 and the CO, et cetera. Shelf is out sort of in this region. All right, Pluto also has a leading and a trailing apex, which is a little unusual for a planet because it orbits a point that's outside of itself. The point that it orbits is the barycenter, which is probably, I just freehanded it on here, but it's somewhere around in there. So Pluto, the rate of motion is very slow. It's like 10 meters per second or something, but it does actually have a leading and trailing hemisphere for what it's worth. OK, so let's put on those locations of the maximum for each of those different volatiles. So there's a bunch of CH4 bands, and they are generally in this range. And the CO was here, and the N2 was there if you fit a sign to it. And if you fit a sign to the shift, they're up and around here. I'm not sure I believe any difference between these. I would basically say that they're on the anti-Charon side. And when I first saw this, I got all excited about the symmetry with the tidal axis and got to thinking about all kinds of things like offset from center of body to center of figure, and is there an altitude control thing going on, like lunar near side, far side dichotomy. Maybe that is, but I don't know, speculation. Soon we will know more. Let's compare to Triton. So Triton's a little bit bigger, and we're again looking down on the summer pole, but this time it's the south pole. But because it goes retrograde around Neptune, the sun rises in the west, and the coordinate system goes the other way around. But the sense of spin, as seen from the pole, still looks the same as what we have here. So let's put its variations, because it's got the same 3 ices on its surface. And they're like this. And and this was in a paper from 2010.
Where's Neptune?
Yeah, right. I meant to say that. So Neptune is to the right. It's defining the 0 degrees. And so Charon's to the right on Pluto. And the trailing is the T indicates the trailing hemisphere. And here it is on Pluto, and that's the leading hemisphere. Yeah, sorry, I meant to say that. So at first, what I got excited about was thinking, oh, wow, OK, so N2 is most concentrated on, the tidal axis. But it's not really. When you actually do the sign fit, it's a little off. But now what I'm seeing that's really weirding me out, and maybe somebody in the room has some clever idea, is that if you take this pattern and you rotate it 140 degrees, you get the exact thing that's on Triton. I mean, that's just weird, especially because I didn't attribute any significance to the configuration here. I just sort of mentally averaged all of those together in my head. But they're in the same order over here, and the same angles pretty much. I mean, it's weird. This is maybe just a coincidence, but scratch your heads and think about it. Maybe the volatile people who are doing GCMs can come up with an excuse for this, but I haven't seen it yet.
None of those volatiles on Pluto be attributed to Charon?
That is correct. And Charon is always in our spectra. We can't do anything about it, but it's basically water ice and some ammonia. And those are non-volatile at the relevant temperatures. There have. Oh, an excellent point. Excellent point. All right, if I can buffer them long enough. All right, so let's move on to, so we've been talking about diurnal variations, basically just plotting everything versus longitude as Pluto rotates. Let's talk about secular variation. We've now accumulated with this instrument, and obviously it's nice to do this stuff with a consistent instrument, because then you don't have to worry about instrumental funnies. We've got about 13 years worth of data on Pluto now. So that's 5% of a Pluto year. So we're really starting to cover a lot of season. So how much would the Earth change in 2.5 weeks? Well, if you're in Arizona and monsoon season kicks in, it can be kind of dramatic. So here's sort of a cartoon schematic of the way Pluto's orbit goes. When it was discovered was down here. Equinox, when the sun was above the equator, and perihelion more or less coincided in the 1980s. Just a coincidence. The time period when we're observing goes from here to here. So we actually covered a fair bit of orbit during that time, just simply because it's close to perihelion where it's moving at its fastest. And even though we have observed less than a full Pluto year of 2.5 centuries, we've actually seen about 180 degrees swept out on the sky. I guess the other thing worth noting is that the sub-Earth, sub-Sun latitude is getting to be pretty high. It's about 50 degrees this year. So it's definitely far from equatorial illumination now. Here's a little bit more 3D view. This is using one of the rendering tools that we use on the New Horizons team to plan the observations, and you can put the Earth as the observer. So here's the way it looked in 2000, and here's the way it looked in 2013. And you can see that high latitude regions were definitely foreshortened back then, and they're more and more coming into view and dominating what you see of the disk. And likewise, low latitude, this is now going in what's going to become the winter hemisphere, is disappearing from view. So there's good geometric reasons that you would expect the surface to change just from geometry alone. Okay, but there's also volatile transport, which is sunlight drives the sublimation of these ices. That puts it into the atmosphere, creates a pressure gradient, which creates winds and blows it around to the night side or to the winter side from the summer to the winter side. Thermal radiation removes the latent heat of condensation and enables you to condense. So there's a bulk transport of volatile material from the sunlit areas to the not sunlit areas. You work the math and you figure out what the rates, how much energy you're getting from the sunlight and how much energy you're losing to thermal emission. And you can estimate that it's of the order of centimeters per Earth year of ice transported. And any of you who have been doing remote sensing of rocky planets know that that's way more than the optical skin depth. It's actually not way more than the optical skin depth on Pluto because some of these materials are very transparent, but it's enough that you would expect to see that you would not be surprised by changes on the time scale of even an Earth year. This was some work that Adrian actually alluded to that John Stansbury and I did back in 2000 or something. And we just looked at, we did a Monte Carlo ray tracing model, and we just looked at where the sunlight would get absorbed, and we compared that to where the thermal emission was coming from. And it's, regardless of the geometry, and pretty much regardless of the texture of the surface, for those materials, whoa, let me try that again. Where am I now? Okay, okay, you don't tap the mouse, you just slide it. The thermal emission is stronger in the immediate surface, first few centimeters, and the solar absorption is almost universally deeper. And what that means is that energy is being absorbed a little bit below the surface, and it's being emitted from closer to the surface. This was the old solid-state greenhouse idea that's been around for decades and decades. But it's pretty much got to happen here. And because they're volatile, you can fix the heat imbalance by just having bulk flow of material if the surface is porous enough. And so what are you doing? Well, you'd be hollowing it out down here and condensing more stuff up there. Sort of strange. I don't know what kind of geology. Unfortunately, this is only at centimeter scale, so we're not going to see it from the spacecraft, but maybe there is some macroscopic expression of it. Anyway, my point in throwing this slide in was mostly that, the 1 centimeter bulk volatile transport is a little more complicated than just removing a centimeter off the surface. And it's not really the case that it's the optically uppermost layer that's doing it even necessarily. It might be coming from just a little bit below the optically active layer that you're remote sensing. All right, so now instead of plotting longitudes, let's throw away a bunch of points. So what we're doing is we're going to pick out just the points that were taken first at the lowest latitude and just the ones that were taken last at the highest latitude, and just plot those. And I'm going to look at one band so I can zoom out the scale. And this is what it looks like. This was the ones that were in 2001 and 2002, and these were the ones that were 2011, 2012. And we had an instrument at Lowell in the 1990s at our little 1.7 meter telescope that could also do Pluto, and we really banged away at it a lot and got a lot of nights in 1998. I basically lived out at the telescope just about. And you can see it's changing pretty dramatically from over a time scale of years to decades. And it's not consistent with longitude. It's, some longitudes, like, all right. All right, that's quite live, this mouse. Some longitudes are changing a lot, and other longitudes are changing relatively little. All right, so trying to get an idea of what the, is it linear with time? Is it geometry, or is it volatile transport? That's really what I'm trying to get at. So what I did was I plot the envelope from each of several bins where I had enough data to fit a Fourier function to it. So going back once, you see the dashed lines through it, that's a Fourier function fitted to it, which may or may not be a good representation, but you can at least limit the bandwidth to what a rotating planet might plausibly be able to give you. All right, so now I'm basically here, I'm plotting the envelope. So I'm plotting the mean and the min and the max of the Fourier function. And it sort of looks like things were moving especially fast right in this period. And this period we were interested in because Mark Bowie, from photometry, light curves, and stuff like that, thinks that some dramatic change started right around then. Unfortunately, this is a different instrument. This is this OSIRIS instrument at Lowell, and this is the IRTF specs. And you'd never really trust it if you change the instrument, because the spectral resolution is different. The procedures are different. Who knows? But this was attempting to make them as consistent as possible by degrading the resolution of the one to match the resolution of the other. And so it's certainly consistent with something interesting having happened in the early 2000s. What about the CO and the N2 ices? Well, at the time of the Icarus paper, which was not that long ago, it just came out a few months ago, what I did was I binned, it didn't look like anything when I color-coded them, by year. And so what I did was I binned 2001 to 2006, and I binned 2007 to 2012, and fit signs to the two. And those are almost invisible here, unfortunately. There's a dashed blue line for the later ones and a dashed red line. And it looks like it declined a little bit, not statistically significant. The nitrogen looked like it declined more. But that's where we left it then. So what is it? Is it geometry or volatile transport? Well, there is one other trick that we could try, which takes advantage of the fact that, I've got to really watch it on those thin lines. The parallax from the Earth's motion around the sun modulates the shift in sub-Earth latitude that's seen on Pluto. And so this sinusoid is the trajectory of the sub-Earth latitude on Pluto over time. You can't look at Pluto when it's on the other side of the sun. So basically from quadrature to quadrature is the green part. That would be where you could plausibly observe Pluto. And this is where we did observe Pluto. And the gap in that year is quite unfortunate, but I was too lazy to get an observing proposal in. And I feel guilty if I haven't actually already published something. And so Kathy Olkin helped me overcome that guilt, and she took charge of sending in the proposals afterwards, and that's why the coverage gets better. And you'll notice one thing here is that you can actually match the latitude, in 2 consecutive years, right? Because of this parallax from the Earth. So we took advantage of that, and basically, and also IRTF's willingness to schedule things very creatively, and matched not just the latitude, but also matched the longitudes of some existing observations. We ended up with 3 of them where we matched it. And these are the circled ones here. And so if it was geometry that was doing it, when you've now controlled for geometry, you should see no change, right? If it's volatile transport that's doing it, you should see a change that's consistent with that time interval, which is a relatively short time interval, so you're trying to detect a small signal, but you give it your best shot. All right, so, well, I just said that, I guess. So those are the predictions. So what do we actually see? Well, on CO and N2, we basically saw no change. So it looked consistent with geometry. But it wasn't very statistically constraining, so it didn't really rule out some volatile transport contribution. On methane, we saw something unexpected, which was that it changed in the opposite direction from the long-term trend. And so at first, that was a bit of a head-scratcher, but you could make that by having both act at the same time and go in opposite directions, right? So if geometry is giving you more methane as you see more of the polar regions, but volatile transport is making it go away, you now suppress geometry and all you see is the going away signature. So basically, you're seeing more of the pole, but the methane is being removed from the pole or hidden somehow or other by change of texture or who knows what. So that's kind of interesting. So that's kind of where we were at the time of the Icarus paper, but we got now new observations in 2013. And so here's there's where we stood at the time of the paper. Here's the 2013 CO data. And when I saw the first 5 of these, I was like, boy, they're all low. What's going on? And we got 2 more, and they're all low. So it really is changing it pretty dramatically just in the last year. And so what I did was I went back and I took that sine wave and I slid it up and down to minimize chi-squared every year where there was multiple observations. And so I can make a plot year by year, and this is what I got. And so here's that 2003 point, much lower than everything else. And you can see the way I had binned it earlier was perhaps unfortunate because I basically straddled the peak, it looks like, and got one of my bins on either side of the peak. And so it's maybe not surprising that I didn't see a whole lot of difference between the two.
Is this globally integrated?
Yeah. Now, of course, our sampling is a few random nights each year, and what longitudes they're at, we don't have any control over, so we take what we can get. Sorry, I forgot to repeat the question, which was whether it was globally integrated. It strives to be globally integrated. All right, so I wanted to say just a few words at the end about thermodynamics and some of the lab work that I've been doing. So there's a nice artist picture of what mysterious processes might be going on Pluto. But what I really want to do is draw your attention to the vapor pressures. So our best analog for volatile geology is the polar regions of Mars, just simply because we have great imagery and observations of those. But on Mars, it's basically CO2, and there's water. And look at the difference. These are orders of magnitude, again, the small ticks. There is a big difference between the volatility of water and CO2. You come over here to Pluto temperatures, around 40 Kelvin, and here's 4 different species that are all within a few orders of magnitude of each other in vapor pressure or volatility. They're going to be getting together and forming materials that have more than one ingredient in it. And that, that's alloys, that's metals. Very complicated things happen there. We have a phase diagram for a lot of the binary systems, but we don't even have phase diagrams for the ternary or 4-way system. So we don't even know what phases are present. We need to do that lab work soon. So this is the methane-nitrogen phase diagram, which has been known since the 1980s. It basically tells you what phases are present for a given bulk composition and temperature if you're in thermodynamic equilibrium. So in these regions, you have only one phase that's present. In these regions, 2 phases are present. So if you had an ingredient, you had a bulk composition and a temperature like there, which is plausible for some region on Pluto, what's really present is 2 phases. It'll be these 2 phases at the solubility limits that will be present. And you can use the lever rule to tell you how much of the 2 is present. And that's if it's in thermodynamic equilibrium, which it may or may not be. But from my experience in the lab, stuff reaches equilibrium pretty quickly at these temperatures. And this is an experiment where well, once again, I should have cranked up my gamma a little bit, but where we mixed up something right about here and then cooled it off so that we crossed that solubility limit boundary. And what happens is, as we're cooling, a bulge forms over here as crystals of this other material start to form. and it has a different wavelength. And it's also different from the wavelength of pure methane. So that's this stuff along this solubility curve that we really need to know what it's like. And of course, what would be happening here is you'd start off with some single phase, and as you cool it, methane actually migrates to and forms these methane-rich crystals, and they grow, and who knows what shape they have. And the spacing will have to do with the diffusion rate and how fast you're cooling, and so on and so forth. We don't, so we have to think about all of this when we're doing remote sensing there. And what we really need to be able to interpret what we see, if it was just pure those two ingredients, is all of the compositions as a function of temperature along the solubility limits. And so we just did a huge lab campaign this summer to do that, to actually measure the spectra of all of these components, which you could then use in a mixing model. And these are the shifts that you see relative to pure methane for the two different phases on the two sides of the phase diagram. And they do depend on temperature, and they do depend on composition. So you really need sort of a matrix of things. And this is still only with a binary phase diagram. We haven't even begun to talk about the four-way system. And so how well does it work? Well, OK, so it's hard to see. This was the best that we could do modeling using the way we had been doing it, which was approximating these two components with pure methane and with the Kiriko et al. Highly diluted methane. And it's pretty good, but there's still some little odd residuals that have caused people to get excited about trying to interpret them, because that's what residuals are good for. And this pink curve is the model where we took those two ingredients that we measured in the lab at the solubility limit, and it just goes right down the middle of the points. So I think we're on the right track with this. And we are intending to get this written up and make the data available to the community as fast as we can. And so that's my last slide, which is just reiterate that Pluto's surface is very heterogeneous. I mean, we knew that from the albedo map already, but ingredients are heterogeneous too. And there's sure to be some interesting processes at work using these ingredients, which are capable of moving around on very short timescales. And I think we need to keep monitoring it from the ground as well. Thanks.
If I could start off with the questions, Will. So you've mentioned methane, carbon monoxide, and nitrogen for mobility. What about CO2 ice or other ices on the surface?
So CO2 has never been detected on Pluto, although it has been seen on Triton. And in fact, let me go back. Where's my mouse? There it is. That one. So you can see where the CO2, the strongest features of the CO2 are this triplet here. And there's just nothing corresponding to that on Pluto. So that puts some pretty stringent upper limits on it. I mean, it's probably there. How could it not be? But there's not much of it. Maybe it's just getting buried on seasonal timescales or something like that. And water ice, likewise. So you look at the vapor pressure curve. See if I can find that. And so at Pluto temperatures, maybe the warmest place you could get on Pluto is 60 Kelvin or so. Not very high vapor pressure. Right. It's basically a rock.
Okay. I don't see methanol in there.
You're right.
Why
I should add that. It's got to be between. It's got to be just a little below H2O, right?
Okay.
Well, or I mean, just above H2O.
In that, yeah.
On these
I
units.
think.
Yeah.
Well, actually, I think it might be actually more volatile than CO2. But I could be wrong. I don't know.
I should definitely add that. And I don't think it is more volatile than CO2, but I don't know the numbers off the top of my head. And I should add ethane to that too.
So any correlations or measurements with the surface temperature or temperature homogeneity?
Yeah, so there are several different ways of getting an idea at the surface temperature. One is from an atmospheric model from a stellar occultation. One is thermal emission observations. One is that there are temperature-dependent effects in these spectra. And all of them point to a temperature in the range of high 30s, low 40s. Except for the thermal, which requires at least some regions that are even warmer than that. Emmanuel Lelouch did a couple of papers using Herschel and some other instrument earlier, where he thinks that there must be some regions that are at least 50 or maybe 60. So they must be devoid of nitrogen ice because they're not being vapor pressure buffered.
Hi, over here. This side. So I have a question on origins. You know how like the Earth and the Moon are supposedly from the same part of the solar disk. I was wondering if Charon has been analyzed spectrographically and whether that would show a similar relation between Pluto and Charon. And also I'm kind of curious, since it's so similar to Triton, whether they might have a common origin.
Yeah, so there are separate spectra of Charon, and it basically is dominated by water ice, which is a rock at these temperatures. There's also some ammoniated contribution that makes a weak feature at about 2.2 microns. And how that gets there is not obvious to me, but it's clearly there. But its gravity is probably too weak at these temperatures to hold on to these volatiles. So if they were there, they would be there transiently and they would disappear. So I'm not troubled by the fact that we don't see them there, because they really shouldn't be there. They would be stable. You know, the thermal speeds would exceed escape velocity. Whereas Pluto has enough faster escape velocity that they just can't get off very quickly. But the presence of methane bugs me because it's really readily destroyed by energetic radiation. And so I kind of think that it has to be resupplied from the interior somehow or other. So I think that's... No, I'm talking about methane on Pluto and on Triton. I think that needs to be supplied by some kind of either slowly escaping from clathorates or being created by some chemistry we don't understand, or... Not if they're circular orbits. And they would damp to circular pretty quickly. But we've been struggling. You'll see a long series of papers with me and Mark Bowie and Dave Tholen and all. And we have eccentricities, and then we have circular, and then we have eccentricities. And part of the problem is that they're tidally locked, and Pluto has these huge albedo features. So when you're trying to measure astrometry, and now you've got the bright part towards you, and now you've got the dark part of Pluto towards you, that torques the astrometry, and that looks like an eccentricity. And so it's really tough to do. We think it's circular now, but that's the flavor of the last couple of years.
Yeah, so once you measure the volatility of the surface of Pluto, what are the ramifications or goals of this research? What are you hoping to figure out?
Well, what I want to do is when New Horizons gets there and shows us some kind of landform that's so bizarre that we're all sitting there staring at it, scratching our heads and goes, well, what on earth is that? That we've already started thinking about the processes that are at work, and we can figure it out. And the figuring it out is the fun part for me. That's what I've been living for.
My question is about one of the first charts you showed, the little mug shots of all the Kuiper belt objects. They all look like circles except for the Haumea.
Yeah.
And is that spinning rapidly?
Yes, it is.
Really rapidly?
Yes,
I mean,
really
that's
rapidly.
yeah. Okay, thanks.
Its period is like 3 hours. Does that sound about right?
Wow.
Yeah, this is a great slide. So I'm wondering what gets in the way of doing comparative planetology through ground-based spectroscopy like you were doing for Pluto. What's the obstacle there?
Telescope time. I mean, we are doing that. Steve Tegler led a paper last year where we compared Eris, Pluto, and Triton spectra, where we're looking at the methane bands and the influence of the nitrogen on them. So we're starting to do that. It's just that the geologists can't really jump in until we get close-up pictures. Yes, they are. Yeah, Eris is, it's a big object, but it's like 18th magnitude, 19th magnitude, something like that. So doing spectra of things like this is tough. You need big telescopes.
More questions?
Careful of the wire.
Back to Haumea, do you know how close that is to being a point where it would fall into two pieces?
Yeah, but you can put constraints on the density by the fact that it hasn't fallen apart. But yeah, no, we do know the density now because we have the satellites.
Density's about 4.
Yeah.
So it might be into a film
Okay. So, but what would the spin rate to make it break apart? Do you know? I mean, 2 hours is sort of the number that everybody tosses around, but I'm not sure if that's actually valid here. Okay. Qualar is supposedly pretty high, although it's been creeping downward. The last one I saw was closer to 2.5 or 3 or something. But.
Yeah, this is just kind of a piece to my other question. You said you just want to figure out the processes, but like what are the benefits of knowing these phenomena that's occurring on Pluto if we're here on Earth? Are there is it a possibility that there's extraterrestrial microbes or something to that extent? Or is it just for the sake of knowledge alone?
Well, I think the sake of knowledge alone is sufficient to motivate many of us, but it is not out of the question that Pluto has an interior ocean, and that always gets the exobiologists excited. Now, it might not be the easiest exterior ocean to get to, but so don't hold your breath waiting for a mission to go look at those microbes. But it is possible that Pluto has an interior ocean and could host life, and there's certainly no shortage of organic ingredients out there in the outer solar system.
Well, if you have any further questions for Will, feel free to come up and will we have a special Are We Alone mug? I know you're going to be working hard in the 2015 time period. Feel free to use it with any amount of caffeinated beverage of your choice. Please join me in thanking Will for his great talk.